All right, welcome everyone to this fifth video in our set of lectures here on chapter 14, talking about chemical net kinetics. In this video, we're going to be talking about collision theory, right? So collision theory, as we'll see, will help kind of explain why a chemical reaction rate depends on temperature, okay? And show us, right, we talked about at the very beginning, the very first video here, right, that the rate law, the rate of a chemical reaction does depend on temperature, and that dependence is through the rate constant K, right? And that dependence, we'll see, it can be described and discussed through what's called the collision theory here, okay? So collision theory is that, a theory, okay? Right? And in collision theory, it states, right, for a chemical reaction to occur, right, the molecules must collide to react, which makes sense, right? Things need to react together. They should be close together, right? They should collide, should interact with each other, right? Right? But the reaction rate is not equal to the number of collisions, right? And that's because the second part of collision theory is that the molecules, when they collide, have to collide, right, in the right orientation, and they need to collide with enough energy for their chemical reaction to occur. Right? So let's give an example, right? NO2 reacting with NO2, right, to form NO3 plus NO, right? If these two things collide in a way where I have NO, right, O here, right? If these collide where I have, you know, my oxygens colliding with each other, okay, this is not going to form some chemical reaction to form NO3. So the oxygen doesn't transfer to the other oxygen. This oxygen has to get close enough to collide with that nitrogen for the chemical reaction to take place, okay? And then they need to collide fast enough with enough energy for you to be able to break the bond from one nitrogen and form the bond onto another nitrogen, okay? And so, right, so collision theory, again, states that, right, for a collision to happen, right, molecules have to collide, and have to collide with correct orientation and with the amount of energy needed, right, in order to have an effective collision and the reaction to occur, okay? And that amount of energy needed is referred to as the activation energy, okay? Some energy threshold that you must have, okay? It's called the activation energy. Okay? So often when we give these reaction diagrams, right, we go from reactants to products, okay? And what we have here in this reaction diagram is some barrier for the reaction to occur, okay? And that barrier is going to, what the molecules look like at that barrier is referred to as the transition state. So for example, okay, in our example of, let's just say we're transferring hydrogen. Let's say we have HCl plus fluorine, right, or plus F minus going to Cl minus plus HF, right? We have, like, we're transferring hydrogen in this chemical reaction, right? So, right, while this reaction, for this reaction to take place, right, I got to sort of break that hydrogen bond, right, and then I got to form the bond with the fluorine, right? And so this transition state is going to look something like this, where the hydrogen is kind of partially bonded between the two atoms, right? Right, because again, I got to kind of break my bond before I can form the new bond, and so it takes some energy to do so, and that energy, okay, is given by this activation energy. Okay, so EA here is the activation energy. Okay, so if I think about these things colliding, and I think about this and happening, say, in the gas phase, right, I can talk about how much energy a given molecule has at a given temperature, and that's given by these type of distributions. Okay, so these are given by kind of this Boltzmann distribution. You know, it doesn't matter, right? But basically, what is plotted here is a distribution of the available energy, typically kinetic energy, of a molecule at a given temperature. Okay, So T1 here is a lower temperature than T2, right? Let's say this is 200 Kelvin and this is, say, 300 Kelvin, right? 200 Kelvin is less than 300 Kelvin, right? And so at that lower temperature, more of my molecules have lower energy, okay? Not all of the molecules have the same energy. They have a distribution of energy, okay? At a higher temperature, more molecules have a higher energy in that distribution, right? And what I'm interested in is, let's say I have some activation energy, okay, EA and the activation energy. What I'm concerned about is how many molecules have an energy greater than my activation energy, okay? And at higher temperature, more molecules will have an energy higher than the activation energy. And so that means at higher temperatures, I have more successful collisions, so my rate is faster at higher temperatures, okay? Because let's pretend, right, things collide at the exact same, I have the same number of collisions no matter what the temperature is, right? Well, as I get to higher and higher temperatures, the percentage of those collisions that are successful in producing products increases, okay? Right? And that's just because the percentage of molecules that have an energy greater than the activation energy increase with increasing temperature, okay? Right? So again, at higher temperatures, more collisions have the energy required to get over that activation energy, right? So more collisions are effective, right? That means more effective collisions means I have a faster reaction rate, right? More reactions are happening per some point in time. Okay. And this relationship between activation energy and temperature and our rate constant is given by what's called the Arrhenius equation here. Okay, so this is the natural log of our rate constant K is equal to minus the activation energy divided by R. R here is your ideal gas constant. Okay, right. And then this is multiplied by 1 over the temperature plus the natural log of A. Okay. You notice here that this is an equation for a straight line, right? So if I plot ln of K versus 1 over T, okay, I will get a straight line with some negative slope, right? With the slope here, right, is minus EA over R. Okay. And so this is done often in labs where you will measure the rate constant for different temperatures, and you use that to determine what the activation energy is for that chemical reaction. Okay, and so that is how our reactions depend on the temperature, right? Now the rates depend on the temperature, okay, for our reactions. And again, we can understand this through collision theory, which says, right, for a reaction to happen, things have to collide in correct orientation and have enough energy to overcome the activation barrier, right? The activation energy required for that chemical reaction.